genome-wide skip discovery, single nucleotide polymorphism on 20 varieties. So we worked for several years with different partners, and we provide that material for Susan at Cornell to devise a bigger chip. Right now, currently, we have a chip that can interrogate 700,000 skip positions in the gene. Okay. So these are all like close to sequence. So we're here, and I just find out that the 3,000 genome that we work with BGI is in the air now. I know many people say, oh, you're so slow and so on. Finally, there's all multiple partners involved. Finally, this is copy on the hard drive and flown to you. So I'm very happy to hear that. And then just a few hours ago, Ken gave me this slide. He said, it's real. 3,000 lines data is available, and he constructed this diagram. So it's in our hand. It's coming to our hands. So here's a pre-analysis of using the skip data and showing this dendritic. Okay. Now, so this slide I put it in. I just went to 2 days ago. I went to the Mao lab, Mike Thompson's lab, and I want to take a picture of this thing because there's a initiative by Tom Facero. He's the field lab manager. He worked out a deal with a supporting facility called Genomic Installation, and they sponsor the setup. We provide the housing, we provide the space, and they provide the people and as well as the machines. So this little machine here can generate 10 gigabytes of sequence. I just use it as a demonstration. That 10 gigabytes probably 20 times full of genome sequencing of one variety. We are not at the point that we can use this to sequence our own gene bank. But what I'm trying to demonstrate is this type of technology will become simpler and also higher throughput. So who knows, in a few years, we may be able to do it just as we go along on a daily routine. Just today I do 10, tomorrow I do 20. Right? So I just want to say that this is being tested, and we're looking forward what capacity this lab can do. Okay. So the second thing that I like to mention as an ingredient for the genetic diversity platform is you need just the gene bank material may not be enough. You need specialized stock to help you develop it. So those who are working with me knows how passionate that I am about the magic population. So I take this opportunity to tell you a little bit about the magic population. So we need to ask the question. I mean, it always on my mind that have we used enough genetic recombination ingredient? I think this is a very important question. There are some advocates on recurrent selection. It's about genetic recombination, right? So the magic seems to be a nice compromise between not as heavy as recurrent selection, selection breeding, but rather creating a gene pool that serves breeding and also genetic mapping purpose. So this slide just shows you how you make the magic population. So magic population usually involve 8 founder lines, and if you're interested in breeding, you use an elite line to become your parent. Okay, so you don't want any linkage drag in your parents. So 1 ABC is 8 parents. Now why 8? Because manageable. You can do 16 too, but then they become very tricky to monitor. So to make the first generation, you make F1, and then you cross F1 again. Don't let it settle. Cross F1 again, and repeatedly doing that. So you bring in 2 genomes, 4 genomes, 8 genomes together in one time. Okay? And then you sell down the last round with 8 genomes. And then they have 3 rounds of recombination meiosis, okay? And that's how you make the magic. The multi-parent intermate. Okay? And then you have a bulk material here. And if you go to carbon gate on the left, that's what the magic is. Okay? So right now we have population at the S7 stage, which is equivalent to F8. So they are now ready to go in terms of doing full-scale phenotype and extraction of material for breeding. So I just want to show you that for mapping, just doing that, the magic population allows us to map fairly quickly the interesting trait. So here I show you, this one is a blast-resistant locus on chromosome 9, and just this one just show you the magnified. So you can get down to a level that within a megabase resolution, okay, by association only. And we're only using about 200 lines to have this resolution. And then you can look, you can abiotic stress, the famous one here on chromosome 9, and you have subtolerance on chromosome 1, and then you have the grain quality and so on. So simple, 200 lines, phenotype, output trait, you get this type of data. So that's, and keep that in mind because that's what I want to advocate in the future, is creating gene pool like this so that they're phenotype ready. Okay, they're ready for phenotype, any other trait that of interest to you. So just quickly show you the resolution of the different genes here. The sub1 and so on is 600 kb differences. I mean, meaning you bracket your gene with SNP marker in a 600 kb, no, 600 kb, 600 kb interval. Okay, and then in a high resolution, 130 kb, very decent resolution for the amount of work because you're looking only about 200 lines. Okay, so just a snapshot. I think we want to look at the current one. Oh, this is 2013 last season, meaning last season. Right now we're seeing that it's a new season. So it looks pretty good. So it's not the beta gene or the well-known gene that we're interested in. We're interested in asking the question, can recombination give you better transgressive segregation? Transgressive meaning you go beyond your parent. Okay. So these lines are tested in multiple locations, 3 sites in Philippines, 1 site in Tanzania, and I think we have 1 site in Vietnam. But the data, what we want to I just illustrate is 2 sites, one at Erie and one at Fukinom. The star indicates a check. There's a check position. And then the tail here represents what we want to see. It's a transgressive segregated lines that are out-yielding the check that we put in. This is just a few, just 2 seasons, I think. So not really conclusive, but it's promising. And when you look at this part, the last column, and look at the, don't worry about the table. And these are using the, I'm not very good at this. So technically, the index is called yield stability index, taking into account the yield and stability across environment. Okay, and you can see that all the top 20 all from the magic number. So again, not validated in multiple trials, but very promising. Okay, so the third thing that I like to describe is about the important ingredient in the genetic diversity platform is modernizing phenotype. So if you don't have that, you're missing one leg of your platform. So the phenotyping, I like to emphasize, should be including scope, meaning the type of trait you analyze, and also in scale, the throughput and the number. Okay, we need to modernize it to do that. So you want at multiple levels in terms of scope, molecular, cellular, whole plant field. Okay? And capture phenotype over time in a dynamic way. And possibly non-destructive if possible. And then high throughput. There are probably more criteria you can use. But we need to modernize the way we do phenotyping. So this slide, Steve helped me, providing me a few slides to show you. After 2 years of sort of tingling with the system, so now we have this field phenotyping capacity, not capacity, but this trial that is a tractor driven by GPS, and then holding a boom here with 8 sensors, 8, and then this drive down the bun and then collect data using the sensor. So let me see. I think you've seen this before in my previous presentation in program 1. So what it is, nobody on the drive. Is anyone sitting on the tractor? Nobody. They're not steering, they're driving. So this is the recombinant inbred population interested in biomass. So run along, and it's an 8 plot, and then 3 replicates. So the first time this year, we actually collect data, which I show you in 2 seconds. It took some time, right, to see that these it isn't so long, like the wiggle at the end, and so you have to stabilize it, and so still working on it. It's not easy, but I think it's quite promising. It's very slow speed. It's a real speed then. Okay, so that's just the distraction. So these are data actually. This is the first time we got it. Again, Steve deserves all the credit for that. So this thing I don't even know what it means until I asked. Normalized difference vegetative index. Apparently, it reflects, is correlated in other studies with biomass, with fresh weight and so on. And so these pixels here representing the intensity and scale is here. So you can do 4,000 plots in 2 hours using the tractor. And this is the interesting part. So sure enough, using this data, you have look at correlation with the sensor reading with the manual collected data. One is plant height, fresh weight, and packaging. So you can see very good correlation with plant height, and then decent correlation with fresh weight, which is what we're most interested in, because that's reflect biomass. Not that good with having data. So again, we have a lot more data. It's just the beginning. So it's very interesting to me, and that may be the beginning of trying this out for reading material. So just one slide to indicate, I'm not expert in informatics, but I know that we're putting effort now to collect all this data, the phenotype data, so not just DNA sequence, to integrate them, make it user-friendly, available, archive properly. So we have initiated since last year the International Rights Informatics Consortium, we call it IRIC, and now in the Nick is in the audience. He's leading the charge in formulating this consortium. Okay, so what I want to sort of advocate here is that we sequence the gene bank, make it in silico gene bank or digitalized gene bank, and breeding pool, not just a gene bank, but we should actually do that for all release varieties. So you have a big pool of germplasm that the performance, and then that provides a prediction power on gene and phenotype relationship. And I mentioned that earlier about the GBOX and others. And then I like to emphasize this point. We need a unique gene pool that can be readily phenotyped. That is a package of 400 lines, 200 lines that ship out to different locations to phenotype for traits of interest. And the example is this. if you again drive down to Topham Gate on the left, our magic line, that all of a sudden, out of nowhere, we have this leaf street problem. And they look like, I don't even see it, the top leaf organized early senescence. Right? And then, when you look carefully in the field, there's some healthy one. Okay? So you have this magic population sitting there, showing segregation for you, okay, without natural infection. So my point is that if you have a well-characterized, genotypically, population out in the field, anything happen to them, you observe, are they segregating? Is some are more resistant, some are more susceptible? You right there, you get information about. So this disease, we don't have any resistance. We don't know resistance about this. So we're very excited in the sense that we can go and dig into this variety, this line, and contrast with the susceptible and resistant. So that's why I meant a ready-to-go collection of well-defined germplasm in terms of genotype, and then available for phenotyping Autotrain. So, and we just recently have this email communication. I don't know how it's here or not. He sent an email and saying that their team are able to look at number of traits relevant for direct seed device. So, it just occurred to me that that is the kind of thing that this ready-to-go package of germplasm can be a mobile set, go to our hub in Hyderabad and explore this trait, because they become instantly revealed because they're all genotype. All you need is a phenotyping system allow you to measure the phenotype for this trait. So we can very much target it on its production level, and that to me is a nice way to connect the breeding program. Now this one is a current developing framework for the Strasser phase 3. So the gene discovery pipeline, and that's exactly what I meant. So we have breeding pipeline for Strasser, and this sort of a little bit upstream here. And they no longer upstream, they will be downstream because they will be available, made available for people doing the right thing. So that's why I hope that we have a package of germplasm, not just data, but the real seed that people can use. Okay, so my title is Looking Back. So I'm done with that set of presentation. I'm coming to the end now. Looking back include just looking at the last few years at what we achieved and so on. So this is a summary, but don't read the whole thing. What I'm trying to get is that there are 5 recommendations from the last Center Commission review on our biotech program in 2008, about 5 years ago. And there are only 5 recommendations. Number 2, for instance, genetic diversity platform. I think we truly pursuing that. There's another one here, phenotyping. So we again, we are not necessarily the fastest reacting good, but nonetheless, we see the value and then we're trying to do something. So I think when you look back to this 5 recommendation 5 years later, I think we may get a B+ grade, not necessarily a grade yet, but I took pleasure to see that our team actually pursuing that and actually addressing some of the recommendations. Okay, what is my own outlook? I mean, probably I sort of relayed that in my talk already, but just to summarize it. Genetic diversity, I think, is a key to address current and future problems, and I really believe in that. I think we need to invest in a public genetic diversity platform that can mobilize the global community. So we can't do everything alone, particularly in the area of informatics. But then, if we present a nice platform that people can explore and go to do science in a deep way, there will be people coming to knock it out. That we truly become the preferred partners in doing this. modernizing, phenotyping, novel genetics, informatics. So all areas will attract people. And as I said, I like to see a rapid response genetic results to accelerate the field. So it's like a kit that we can activate. Now, this is my more personal reflection. We're emphasizing the young scientists here. So when I look back on my own work and my own experience in doing research, there are a few key things that I just thought about are important. Find good mentors. Like the reason I use the first two slides, indulge myself, is citing how important they are to good mentors. More than one. Find good ones. Okay? Listen to others. That's very important. Feeling for the organism. This is the title of a book by an autobiography of Barbara McClintock, and the famous scientist who discovered transposal element, right? And I read the book while I was writing a PhD thesis. So this phrase sticks to my mind because you got to know what you're working on, the material, and let the material speak to you. I mean, it's some mistake, but then it's very important to understand the example I gave the first case, the salmon germplasm showing stable resistance. I feel that like that about that variety because we do one experiment, find something, do another experiment, find another. So let the material teach you. Okay? And then I think very important, particularly here at UV, embrace teamwork. And these are my personal experience. You do this, I think you'll be very happy research. Okay, I'd like to acknowledge I can't get all the names, at least my group, I put the name there. They've been very supportive of our lab and so on. And then I work with a lot of people at Geary, and I can only group them bundle them in categories of work: reading, pathology, field genomics. Now I think Paul because and Steve have been driving it. Long-term partner outside Erie, at least research buddies, good friends, and then genetic diversity, the whole team at the GRC and so on. And I need another page just for magic. There's so many people involved. So there's students doing different aspects. This person I need to mention, online, he did well, and he's now doing Nebraska, University of Nebraska, doing genomic selection in wheat. So I've been communicating with him and seeing how he's doing. So he very much the driver of the magic population. So people is everything. I mean, your colleagues and so on. So I like to end with this phrase. I heard it from the Bank International School graduation ceremony from the speech, Victoria's speech, and she said, "I am who I am because of who we are." So, and I feel that working here, that's my sentiment at least, because I can do things because who we are all together. Thank you very much.
Thank you for your nice presentation. It was very informative. I want to ask one question. There are 35 to 50,000 genes. How about finding function of each gene? Isn't that necessary?
No, I think we just over time we'll get there. I mean, there are thousands of genes. I don't think we need to individually do that. I think a phenotyping effort to direct us to the useful team. I'm not going the other way. I think I would say that, that's why I think that if you're creating a germ processing pool, like a cassette type of germ processing pool, provide it to people who need certain traits, and they will discover that. Right? But then what out, I think the public platform should be well documented in silico germ processing pool, Genebank, breeding line, specialized genetic stock. So that to me should be our long-term goal, to establish that platform so anyone can take, because phenotyping is open-ended, right? So for instance, the C4 group looking at the lead anatomy. So no one thought about that, right? So all of a sudden, when you phenotype that, we see QTL controlling the anatomy. So that's what I meant. There are phenotypes that we don't think of now. And I would incline to say that we use phenotype to drive the gene discovery.
Okay, any
Me?
Yes.
Yeah, thanks. Hey, I'll give you an A plus. It's not much more than a B plus. No, that was a wonderful presentation, and I think actually it's probably one of the best that you've ever given in many ways. Yeah. So you're not rusty at all. Yeah. So, but what I want to ask is more related to that question. Now that we seem to have a pretty good grasp on what we really need to do. We've been wrestling with this for quite a while, But I think we have a clear strategy. What I'm hearing and seeing across other CG centers, I think we are ahead of the curve of most, if not of all, probably of all. So where do we still have the biggest gaps in terms of resources that we need to deploy?
I would say that we are pretty good in making genetic stock. So we well known to become an inbred population, and now we're engaged in magic, and we can work with CAP. This is another population similar to magic, the NAM population. So I think that base is pretty good. Then we should continue to expand that, creating specialized people. Like the heat magic, there's someone working on it that you know, and maybe a yield trade magic population. So those are the things I think we should support. The gap, I have to say, is still the informatics. Yeah. So I mean, I'm not just saying it like everyone's saying it, but then realizing we have 3,000 genomes arriving at the airport with a hard drive. What we're going to do, right? I mean, good that I saw Nick at the back here. Good that we have Nick now, and we are champion. And we need to have that capacity by a virtual network, I think. We will never be able to attract a 10 people team in informatics that year. But what we need is a virtual network. And what it means is that you need to be a center of gravity for that type of work, not by your critical mass, but by your data